Guys, how we doing? So today we're just doing clicker questions, and we have quite a lot to make it through, so it might take a while. And then I also want to remind you about this talk. This is on next Tuesday at 4:15 with a reception from 3 to 4. So if you're pre-med, or if you're interested in neuroscience, if you're biology, health science type thing, come hear this fella speak. It'll be in the normal place over in Beauregard 104. And then on Friday, we will have a review for the test, which is on Monday. And so the test will be sort of normal. We're picking up an atmospheric phenomena. That was the mirages, and the sun appears even after it's set because of. Where's that coming from? Oh, it's a legion. Sorry. Gosh. Anyway, what was I saying? Yeah, we have a soundtrack today. All right, so what was I saying? Atmospheric conditions, yeah, and then all the way through the end of the chapter on sound. So 7B, we'll call it. I think actually on the screencast it's called 7C if you're following those on the online class. Let's start with these, though. Some of these are calculations, okay, but they're good indicators of what you might see on the test, so it's good practice for you. Waves propagate along a stretched string with a speed of 8 meters per second. The end of the string is vibrated up and down once every 1.5 seconds. That would be like the period, right? What is the wavelength of the waves that travel along the string? Alrighty. Oh, we'll stop at 45. Okay, good. V is right. So we're going with this idea that V is equal to the wavelength times the frequency. So it's also equal, since the frequency is 1 over the period, it's also equal to the wavelength divided by the period. And so the wavelength, or excuse me, I'm looking for the wavelength. So it's equal to the speed times the period. That's 8 meters per second. Times 1.5 seconds, that's the period. Notice the seconds cancel, and that's equal to 12. All right. Bats can detect objects that are about a wavelength in size. That's the frequency and the speed. Then what is the smallest size insect they can detect with their echolocation? Watch your units. Make sure everything's in SI units, hertz, meters, all that jazz. Okay, doing pretty well so far. All right, let's stop at 105. Okay, good. C is right, 5.5. V, my speed is equal to the wavelength times the frequency. So I solve that for the wavelength, V over F, and that gives me 5.5 times 10 to the minus 3. Being careful to convert this to 60,000 hertz, not 60 hertz, because that's SI units. frequency of a traveling train is increased by a factor of 3, where the velocity is constant, what happens to the amplitude or the wavelength? You increase the frequency by a factor of 3. Almost perfect. All right, let's stop at 48. 48. All right, awesome. That is C is the right answer. Wavelength is 1/3 as big. Remember, we got this expression V equals lambda F. So if F goes up by a factor of 3, this has to go down by a factor of 1/3. So it decreases, it's 1/3 as big. Hey, how do trees get onto the internet? Never thought about that, have you? They log on. All right, gust of wind blows across a field of grain. Tops of the plants sway back and forth. What is that? Is that transverse, longitudinal, polarized, or is it interference of waves? I'm going to stop at 23 or 25. 25. Okay, good. B is right. Remember, longitudinal waves travel back and forth like this, like the hugging wave that we did in class. And the transverse wave is up and down. So when they move side to side, that's a longitudinal wave, and that is a sound wave. Light, on the other hand, is a transverse wave, or it's a little bit different from sound. It's electromagnetic. All right. For a wave on the ocean, the amplitude is what? All right, let's stop at 35. 35. All right, awesome. C is right. It's 1/2 the different. You'll need to know your basic properties of waves. You'll have some questions like this. So if I give you a wave, the wavelength is this distance. The amplitude is this distance. Or you can think of it as twice the amplitude is that distance from a peak to a trough. So the answer is C. What is the wavelength for this wave? Again, watch your units. Meg, I remember, is million. Looks like y'all are getting this all right. We'll stop in about 10 seconds. Stop at 45, 45. Okay, good. What was the answer? D. Yeah, so D is 2.78, like we had before. V equals lambda F. We're looking for lambda, so it's V over F. All right. Hey, where does sick folks go? No, not the hospital. The doc. Like the doctor, it's short for doctor, but it's the doc. You don't even get it? Where do sick folks go?
I thought you said sick folks.
Folks? No, I said boats. Boats. Now it's funny, right? Okay, this is a little more complicated. So a 2-meter long piano string, a mass 10 grams, is under a tension of 338 newtons. Find the velocity with which it travels on this spring. And don't forget, you have this expression for the frequency. I'm going to give it to you. It's on your equation sheet, but it's 1 over 2L square root of T over mu. Remember, mu is my linear mass density. That's the mass per unit. Don't forget that 10 grams is equal to 0.01 kilograms. And so you'll need to find your linear mass density given the mass of the string, length of the string. All right. There's about 15 or 20 more seconds. Stop at 2 minutes. At 2 minutes, 10 more seconds. Guess if you're not sure, 3 more seconds. Okay, awesome. You'll probably see a problem like this on the exam, but B is the right answer. You have to do a couple things. First, you have to find mu. 0.01 divided by 2 meters. That's 0.005 kilograms per meter. Goodness bless you. And then we solve for the frequency. That's 1 over 2 times 2 meters. That's the length. Square root of T, which is 338. Divided by mu, which is 0.005. And that gives me my frequency, which I get to be 65 hertz. And then I find the velocity. V is equal to lambda times F. And then you say, shoot, I don't know what the wavelength is, right? But we assume that we're dealing with our first overtone, that fundamental frequency. And so if I have my string, then my wave looks like this. Remember our waves, how we have nodes on either end? And that means that 2 meters is equal to 1/2 of the wavelength. Okay, on a closed tube, or a string is like a closed tube. Remember we did those resonances? And so in that case, my wavelength is going to be 4 meters. My frequency is 65 hertz. And so that's going to be 260. Is that what we put, B? Yes, okay, so B is right. All right, so a couple things you have to do here. You have to find the linear mass density and calculate the frequency. But then you have to realize that I'm dealing with this first tone, and that my wavelength then is going to be 4 meters, which is twice the length of the string. I was afraid you were going to ask that. How do you know you're dealing with the first tone? I don't know. I guess I'd have to tell you. I'll tell you. You're welcome. Yeah, because the question just went through my head. And I was just going to go on to the next question. But so thank you for asking, Maggie. You're awesome. Okay, we're going to skip this problem completely, okay? So you can just put a big X through it. Go back to that equation I gave you. If you increase the tension by a factor of 2, by what factor does the wave velocity change? Now it'll change the frequency in some way, and then it'll also change the wave velocity. Changes the wave velocity because our wavelength is going to remain the same because the length of your string remains the same. Yeah. All right, guys, just a few more seconds. Let's stop at 133, 133. Okay, B is right. B is right, yeah. So I have F is equal to 1 over 2L square root of T over mu. And so I'm increasing the tension by a factor of 2. That means I have a square root of 2 over here by my frequency, which, by the way, is equal to 1.4. And so if I have V is equal to lambda times F, if I increase my frequency by root 2, then I'm also increasing my speed by root 2. Remember, the wavelength is going to remain the same. And this goes back to our resonances in our tubes. Now, we did the open-closed tube. That was the one that looked like this, remember? And we had waves that looked like this, where the tube was a quarter wavelength long in my first resonance. But then we also did closed tubes, where my wave looks like this. And in this case, the length of the tube is equal to half the wavelength of the wave. And for a string acts the same as a closed tube, because the string is stationary on either end. So you can think of those as nodes or antinodes on the end of a string. Those are nodes, right, where the wave doesn't move up and down, instead it's stationary. So a string operates the same way, exactly the same way actually, as a closed tube, a resonance tube. Okay? Is that a little more clear? I got 4. So in the previous question, we had the, what was it? The length here was 2 meters. And so since the length is equal to a half a wavelength, that means that the wavelength, solving that for lambda, is equal to 4 meters. Because half of 4 is equal to 2. All right? That's a good question. A lot of people play it. A little more clear, y'all? All right. All right, tripling the tension in the string does what? To the wave velocity. So similar to what we had before. If I triple it, what happens? All right, let's stop at 35. 35. Okay, good. C is right, because the same way, F is 1 over 2L square root of T over mu. If I have a factor of 3 here, it means I have a factor of root 3 over here. And then V is equal to lambda F. If I increase this by a factor of root 3, then I increase this by a factor of root 3. And the square root of 3 is 1.73. Okay, so just, we've done this a lot in this class. Look at these equations and ask if I change one variable, how does it affect the other variable? But in this case, it's two steps, because you have to figure out the frequency first, and then how that affects the wave velocity. Remember, though, usually with waves, if you change the frequency, the wave velocity doesn't change. What you're actually changing here is the medium. When you increase the tension in the string, you're actually affecting the medium, and then that changes the speed of the wave, and then that affects the frequency. So be careful that we get our order of actually what's causing what. But you're actually changing the medium, and then that changes the frequency. I'm just going to show you this one. This one's very similar. So F is 1 over 2L, square root of T over mu. Here, you're tripling the density. So I'm tripling this, and then that gives me 1 over root 3. And so just like we had before, V is equal to lambda times F, 1 over root 3, 1 over root 3, and that's equal to 0.58, I think. Yeah, 0.58. That's what this is equal to. So same process there. We okay with that? I have a lot of questions. I'm going to skip over a few. Okay, this is fairly important. Remember our intensity. Our intensity is our power over our area. And here I want to know what is, I give you the intensity, the sound intensity, not the intensity level, that's different, that's in decibels. This is the actual intensity, which is power over area. And I give you the radius of the distance from the point source. Do y'all know the area of a sphere? Who knows the area of a sphere? 4 pi. No, Tyler, you're right. 4 pi r squared. All right, 4 pi r squared. You're thinking volume, and I think you were thinking something else. So, perimeter, I think. All right, so the area of a sphere is equal to 4 pi r squared. I'm pretty sure that's on your equation sheet up in the little top corner. Am I right? It's on the equation sheet? Yeah, it's up in the top right corner. All right, let's stop at 150. 150 looks like y'all done pretty well. 150. Okay, good. B is right. Hey, why did the baker marry the baseball player? To get a better batter. Who sent me that one? That's a good one. Who sent it to me? Was it you? Thank you. I like that. All right. So the power, I want to know what the power is. So that's the intensity times the area. That's going to be 0.5 watts per meter squared times 4 pi r squared. So that's 2 pi times 25. 6 times 25 is, what was the answer? Was it B? Is that right? It was B? Yeah. All right. Let's go to sound intensity levels. These are sometimes confusing for people, but remember our rules. The intensity of a sound, not the intensity level, but the intensity is 100 times that of wave A to wave B. What is the sound intensity level like? Wave A to wave B. Is it 2 decibels below? 2 decibels above, 10, 20, or 100 decibels above. Remember our general rule with this, that when we're talking about decibels, a change, or a change in 10 decibels, increasing by 10 decibels, indicates a factor of 10 increase in intensity. Plus 10 in decibels means a factor of 10 in intensity. Okay, we're sort of on track. Let's stop at 120. 120. Yeah, okay, so D is the right answer. Don't sweat it, you'll get it on the test. But so if I have a 10 decibel sound, something that's 10 decibels above, that means it's a factor of 10 times the intensity level. If I have plus 20 decibels, that means it's times 100. If I have plus 30 decibels, that means the intensity is times what? 1,000, right. If I have plus 40 decibels, 10,000, and on and on. If I increase my intensity level by 10, I add 10 to it, I increase my intensity by a factor of 10. Okay? So you might see some questions like that where you just have to know that that type of scale works. You probably will see a question like that. All right, so here it's a little bit different. You have this equation, I gave it to you. I'm going to give it to you again here. I1 over I2 is equal to 10. Oh, wait, no, I'm sorry. Never mind. No. Never mind. You don't need this right now. It's for the next one. Forget I said that. Go forward to what you're doing. Okay, you're doing great. I'm going to stop at 50. Good job. Hey, what did the seismologist say when he messed up? You know? Not my fault. Right, seismologist's fault, tectonic plates, all that business. Okay, so the intensity was 6 microwatts per square centimeter. Then it's raised by 10 decibels. That means it's multiplied by a factor of 10. So the answer is 6, right, A? If it was 20 decibels, it would be 600. If it was 30 decibels, it would be 6,000. And on and on. If it's 40 decibels, it would be 60,000 microwatts per square centimeter. All right, now on this one, you're going to need this equation that I gave you in class. It has to do with logarithms. This allows us to compare the intensities of 2 different sounds. You need to think about it's not a simple plug-in in the numbers, but that will help you start on it. All right, let's stop at 130. All right, so this is what I want to know. D, that's pretty good. D is right. That's what I want to know. I'm 1 meter from the source, and then I want to know how far away am I if the sound level is down by 14 decibels. So the first question I want to ask is just how different is I1 and I2? What is the ratio of I1 to I2? So we say this is equal to 10 over 1.4. That's 14 over 10, and so that's equal to 25. Actually, it's 10 to the minus 1.4, so it'd be 1 over 25. You follow? That the two intensities of the sound at this point and at this point are off by a factor of 25. And so then we ask ourselves, well, I is power over area, that's 4 pi r squared. By how much do I have to increase r in order to make the intensity go down by a factor of 25? Well, I have to increase it by a factor of 5. I was at 1 meter, so that means I have to be at 5 meters. Let me step back through that again, okay? So we want to start here and ask ourselves, with 14 decibels difference between these two sounds, what is their difference, or what is the ratio of their two intensities? Either 10 to the 14 over 10, 10 to the 1.4. You should have a y to the x button, or if you have a ti, it's usually 10 to 1.4. That's equal to 25, is the decimal number, but you round it off to 25. And so that means that out here my intensity is 25 times lower than it is here. In order to get a sound that has an intensity that's 25 times lower, I have to be 5 times the distance away. Since r is 1 meter, at this point, 5 times 1 meter is 5 meters. That's a little tricky, but you could see a question like that on the test. Try not to shake it up too much, but I do want you to understand logarithms are decibels and how they operate in that way. All right, this has to do with, was it interference of waves? These two waves, they come together, and I want to know at 6 seconds, what do they look like? So think about, where are the waves after 6 seconds? They're traveling at 1 meter per second. So where are they located after 6 seconds? And what do those two waves look like when they come together at 6 seconds? How far do they travel in 6 seconds? They travel 6 meters, right? So this one travels, let's see, that's at 2 right there, so that peak is going to be at 8. And then think about, where is this one? This one's at 18, so that peak is going to be here. And then what does the wave look like when it comes together? Look, I'm going to draw the first wave for you. After traveling 6 meters, the peak is going to be right here, so it's going to look something like this. All right, that will be its position after 6 seconds. And then where's the next one after 6 seconds? And what is the combination of the two waves? All right, let's stop at 135. 135. Okay, good. C is right. So my other wave peaks, well, let's see, I think I have a picture of it here. Yeah, there we go. So my two waves, here's the first one, it peaks at 8. The other one peaks at 12. And they will combine to give us a wave that looks like this, with constructive interference. Open tube supports standing waves at 300 and 400 hertz, and at no frequencies in between. What is the second harmonic of this tube? Now, let me remind you that the frequency for an open tube is equal to N times V over 2L. That's for an open tube. We found that when we drew all the open tube scenarios, and that's on your equation sheet. But think about what that means as regards to the harmonics. If I have a harmonic at 300 and 400, where's the second harmonic? All right, let's stop at 135. 135. Okay, good. D is right. It has to be D because if I have a harmonic at 300 and then at 400 and nothing in between, if I go, so I have a difference of 100 hertz, that means I'm also going to have a harmonic at 200 hertz, and I'll have a harmonic at 100 hertz, and then that has to be the first harmonic, because I can't have a frequency of 0 hertz. That just doesn't make any sense. So I have my first frequency at 100, my second frequency at 200, and then my third and fourth at 3 and 400. So my second harmonic is going to be 200. If I ask for this first harmonic, it would be 100. If I ask for the fifth harmonic, it would be 500. That sort of jazz. Y'all follow why it has to be that? Because there's 100 in between and there are no harmonics in between 3 and 400. Because this frequency increases as an integer value. Remember, n is 1, 2, 3, 4. Okay, here I have two sound waves being produced, and I want to move speaker 1 in order to get constructive interference. How much do I have to move it? By what amount and what direction? To the left or right? A half or 1 meter? And do I move it to the right or the left? Or does this already have constructive interference? But you know that it doesn't, right? Because to get constructive interference, my feet would have to line up with my feet, and that's not the case. Folks. Let's do about 103, 103, 103. Okay, good. You have to move that one backwards to the left. Move speaker 1 backwards to the left of a half a meter. That would be this distance. And when you do that, when you move this thing back, what you get is that this peak is now right here. Right. A half a meter is 1/4 of this total wavelength. And you want to move this peak back here 1/4 wavelength so that the peak lines up there. These other scenarios don't give you constructive interference. They don't add up right. Okay, y'all with me on this? You're going to see some constructive and destructive stuff interference, because we've seen it in both chapters, so you'll probably have at least 2 questions that are dealing with it. What is the phase difference between 2 waves to undergo constructive interference? What must be their phase difference to undergo constructive interference? All right, let's stop at 45. 45. Okay, good. D is right. You need zero phase difference. There were some other questions on phase difference in the previous chapter. Make sure you take a look at those. I don't like that question really. We got two loudspeakers in phase. They emit equal amplitude sound waves. The point indicated, you get a constructive, destructive, or something in between. Okay, good. We'll stop at 40. I can understand some of the answer here is A, and some of you are putting 3, C. And I understand why you're putting that, because when we're dealing with diffraction gratings and the double slit experiment, that we get constructive interference, but it's something less than what we get in the middle. And you're right about that. It's a poorly worded question, but the answer here is intended to be A. So y'all put A, okay? Y'all follow what I'm saying? Like with the double slit experiment, that's what this is basically, except with sound, that we get a really bright spot or a really loud sound right here, and you would get the same thing with these speakers, and then you would get a slightly decreased sound, but it would still be called, a bright spot. It's not a bright spot, but it's, a loud sound. So I can understand why you put C, but we're going to put A instead. I'll stop at 135. Somebody's holding on to that C, aren't you? I understand. Like when you stick with it, you want to stick with it. That's okay. Yeah, well, here with our double slit, right? This is a double slit, basically. With a double slit, we had a really bright spot in the middle, and then we had dark spots followed by bright spots. And each time we had these, it was because the light waves traveled a certain distance, and they were separated by one wavelength. Their path length difference was equal to one wavelength. And here, this one travels 9.5 meters, this one travels 8.5 meters, which they're separated, their path length difference by 1 meter, which is the wavelength of these two sources of sound. And so their path length difference is one full wavelength, so they're going to undergo constructive interference. It's like I have a wave that's here, and then I have a wave that's here. That's not going. I'm offset by one wavelength, so my new wave starts over here. So my peaks and my peaks will line up, my troughs and my troughs line up. When I'm separated by a path length difference of one wavelength, I get constructive interference. And that's what we have here. Okie dokie? Yeah. Look back at the previous chapter. Chapter 8, we dealt with this a lot too. So, like I said, you're going to see similar things. We're almost done. You hear 3 beats per second when 2 sound tones are generated. One of the tones is 610. What is the other tone? All right, we'll stop at 40. We'll stop at 40. Okay, good. E is right. It's either 2 or 3. Remember my frequency, my beats, if I have 3 beats per second, that means it's either combining with a 613 or with a 607 to get you 3 beats per second. So that's either 2 or 3. What are the points that never move on a string? the points that never move. And you can also think of this as the closed end of a tube, right? They would also get this there, or on the ends of a string like a guitar string where it's attached. We'll stop at 30. Okay, good. C is right. Nodes. Antinodes, remember, are those places where you have maximum amplitude in your wave. Like at the end of an open tube or a string that's not attached. You play two waves of similar frequencies. You hear that wah, wah, wah. What is that called? All right, we'll stop at 25, 25. And A is right. Those are called beats. Right? Frequency of the beats is the difference in the two frequencies. Let's see. Actually, I'm just going to tell you this. I said it in class, but these are called normal modes. The various possible standing waves on a string. Those are those different resonance frequencies, and those are called normal modes. I'm going to tell you this one too. It's C is the right answer. The frequency of the third harmonic is 3 times the frequency of the fundamental. Huh? It goes back to our frequencies are given by that n. What was it? N times n what? I forget. NV over 2L, yeah. And so my third harmonic is 3 times the harmonic of my first harmonic. N goes as 1, 2, 3. All right, guys, listen. The second one. So on Friday we'll have a review through the test. So go over it between now and then and just sort of get a survey of what you're struggling in. And that way we can focus on that. It really helps if you have questions. Okay? I'll see you Friday and then the test on Monday. Have a good day. Oh, there is an assessment on the tutor that's due next Wednesday. That assessment counts as 5 points of extra credit. So please do that. Please do it thoughtfully too, okay? Like spend time on the questions.